also everyone for joining us today. So welcome to the Engineering Africa session today. It is hosted by the IEEE Kenya Section Industry Engagement Team. My name is Lumumba Avin, and I'm the team lead. So you might be asking, who are we and what do we do? The Industry Engagement Committee is an arm of IEEE that facilitates, number one, interaction with industries and industry partners on behalf of IEEE in Kenya. We identify gaps, act on opportunities, recommend and launch partnership initiatives between ourselves as IEEE Kenya section and industry partners. So we do this through workshops, industry visits, project involvements, among other approaches to achieve our mission, which is advancing technology for humanity. We are always open to discuss on how we can collaborate, including for such sessions as this. So feel free to shoot us an email through industry@ieeekenya.or.ke. That is industry@ieeekenya.or.ke. Also, we are social, so follow us and interact with us online. You can find us on all platforms, YouTube, LinkedIn, Facebook, and Twitter as Industry Engagement Kenya. That is Industry Engagement Kenya. So thank you so much for joining us today. I'll hand it over to Newton to welcome our guest for today's session.
Yeah, thank you, Mr. Chair. Thank you again. And today we are going to have a session with our guest of the day, Engineer Zimba, who has worked with interconnected power pools for quite some time. So, Bwana Zimba, you're welcome. Feel free to proceed.
Thank you. Allow me quickly to share my piece. Okay, so to my audience, greetings from Harare. I'm sitting in Harare, Zimbabwe. It's quite an honor and a privilege for me to be part of this event. And I do thank the IEEE Kenya section for inviting me to share my experiences to do with interconnected electric power system operations. My name is Engineer Zimba. I'm a member of the IEEE, and I'm also registered as a professional engineer in Malawi, MEI in Zimbabwe, ECZ, in South Africa, EXA, and also in the UK, I'm registered as a chartered engineer, Engineering Council of the UK. Once again, it's my pleasure for me to share my experiences. I'll start with an introduction. I've been in engineering school, I was thinking this morning, for I think 9 years. My undergraduate program took about close to 6 years, then the post about 3 years. But there was no module in the engineering school which was teaching us history. One of my classmates were actually celebrating that we are done with history, no more memorizing. We are now into engineering and science. But over the years, I've come to know that there is a value in history. AFSEC, a body for standards, is busy now developing standards for low voltage distribution. In the 1860s, 1870s, there was a battle between AC and DC. That was the time when the generators were being invented. A lot happened in the 1880s. Eventually, subsequently, of course, AC won because of the three-phase, and also that we can transform power to higher voltage, transmit with low losses. So AC won over DC. There is a lot we can learn from history. We see here that in 1987, that's when the first three-phase AC generator was built in Germany by the gentleman you see there. I would think it was a small generator in terms of power capacity, MVA. Now, the beginning of connection started at that very time. You've got a generator with a smaller capacity, and then it lights your village or your town. Some people would like to bring more lights. In that case, do you retrofit your smaller generator to come up with a bigger one? Or do you shut it down and build another one? So there was a need to connect generators as the load was growing. If you've got 2 generators, they share a load. You can take out one for maintenance. Even when it develops a fault, you can do the repairs. So that was the very beginning of connecting the generators. And the parameters to match when it's synchronizing are power frequency, like I've set there, power frequency, phase angle, phase sequence, and also the waveform. So to achieve continuity of power supply amidst outages, there is need to connect generators, 2 or more. In that case, you handle the load variability. If it's growing, you switch on another generator. They're synchronized. And then in terms of the resource, when the load grows, there is a limit to the capacity, the power capacity of the generator you can build. So if you build smaller ones, distribute them, all the better. You can also choose your own speed in revs per minute. It can be running at a slower speed, but still achieving 50 hertz, and you calculate and set the number of poles. I've put a table here showing growth of loads in the Southern African region. We'll see in South Africa, the lowest low there, the demand in 2010 was 35.85 gigawatt. We can't have one big generator of 35.85 gigawatt capacity. Hence, we need smaller ones interconnected. So as an introduction, this was the basis of connecting power systems. Going forward, I just want to give some key definitions as we start. The first one is of the interconnected power system. What's an interconnected power system? Basically, this is when electrical equipment is connected at a transmission voltage level. Transmission voltage level, to emphasize. And then usually the interconnection is synchronous. They share the same power frequency. But where there are HVDC lines, it may be asynchronous, with on one side a different frequency. Of course, both targeting 50 hertz in our region. In the US, their nominal is 60 hertz, also in Japan, South America. But in Europe, generally, it's 50 hertz, and here in Africa. Then what's a power pool? It's more like now a corporate body where organized electric power utilities operating and developing interconnected power systems in a coordinated manner, and they usually have an energy trading arrangement. Examples are the Southern African Power Pool. Actually, that's where I belong. We've also got the East Africa Power Pool, West Africa Power Pool. In Europe, they've got the ENTSOE. It's also a power pool. Then searching from Google, there was one who was quoted saying, the North American electric grid is the largest and most complicated machine ever built by man. You can imagine all these generators connected at synchronous speed, all these loads, motors for the whole of North America. So they interact and they're like one big machine. So in our region, also in the Southern Africa, we've also got our biggest machine, which is our interconnected power system. And I'm the operations engineer for this interconnected power system. And I look forward to the time when in future, I may be telling my grandchildren that at one point, I was the operations engineer of the biggest machine in Southern Africa, because at that level, you tend to inspire your children. You may say I was a great footballer, even when maybe you were not. For me, it will not be a lie. I'm the operations engineer of this big machine. We'll see that Angola is yet to be interconnected. Same with TANESCO, Tanzania. And yet these two have got surplus generation. We can't wait to have them interconnected so that we utilize their capacities. Most of the countries in Southern Africa currently have got a deficit of power supply. It's unlike in East Africa. When we went to Uganda, we learned that most East African countries have got surplus generation. There is no load shedding there, which is good. Now, what are the advantages and challenges of interconnected electric power systems? I will start with the advantages. The first one is that we optimize the energy resources and we reduce the overall cost of supplying the customer load. I'll be giving examples from Southern Africa, because that's where I'm from. Mozambique, they built a big power station, about 2,000 megawatts, at a time when their national load was very small, maybe less than 400 megawatts. But the resources were optimized. That power was sent across border to South Africa and other countries, neighboring countries. So that's one of the advantages of interconnecting. Then the consumers also access cheaper electricity through bilateral or competitive market arrangements. In our competitive markets in SAPP, during off-peak, the cost of a kilowatt hour is as low as around 2 US cents, whereas the national tariff is around 9. So if you participate on this market, you reduce your cost of accessing electric power. For our competitive market, we also base our pricing on what we call marginal cost. This is the change in total cost for an equivalent change in quantity. So if we look at wind generators, everything, the capital cost has already been met. It will only take wind to blow to generate an extra kilowatt for an hour, for example. In which case, the marginal cost is around 0. I will not say it's 0, but it's around 0. There is no need for fuel to run that generator. So based on this strategy, the rates for competitive markets are on the lower side. And with this mix, we can take advantage of those cheaper generation technologies like hydro, solar, nuclear, to offset the slightly more expensive, like the coal, these fossil fuel technologies. Now, proceeding with advantages, we also reduce the overall impact on the environment. Like someone said, we borrow this environment from the future generation. We need to take care of it for the future generations. So when we are interconnected, you see some technologies emit more carbon gases, while others do not. So as a region, the average might be midway, which is an advantage of an interconnected power system. Due to impacts of environmental degradation, we've seen now that there is extreme adverse weather conditions like cyclones. The two pictures which I've put here, they are from Mozambique during the cyclone Idai. It affected the power supply in the region. We did a paper which we presented at Power Africa Conference, IEEE. You can search, you'll find it. So in Africa, we are less prepared to mitigate these adverse weather conditions. We need to take care of the environment. One way is by interconnecting. Going forward on the advantages, you see here I've put a picture of this big truck. The first time I used this slide, one of my friends was in the audience, Elisha. So I did ask him, Elisha, have you seen this big truck? Do you know that there is a bed in there? And what's the use of that bed? On a lighter note. So this big truck, you see there are bumps there. But when you are in this big truck, you won't feel them. But this small beetle, it will feel all those humps and bumps. And when you stop suddenly, you see this cartoon, you were also traveling at that velocity. You stop suddenly, you still be pulling on your belts. So to the power systems, what happens is when a generator trips, there is a big inertia. The frequency will not dip that high. The system is likely not to collapse. When I started working, our biggest generator was 26 megawatts. It trips, it brings national blackout. It shakes the entire national power grid. But in the region, when it's interconnected, we've been losing a 930 megawatt generator unit from South Africa. The frequency only dipped to 49.49, and then it was quickly brought back to temporal steady state, then back into the normal band. That's the advantage of interconnecting. The system is very strong. Generators can trip, but the customers will not feel the shock. There is also diversity and capability to meet peak load. In Mozambique, their peak is in summer due to air conditioning. The rest of the region here in Southern Africa, the peak is in winter due to heating. So in summer, others can generate more. We will not strain the network if we all were to peak at the same time. So that's diversity. The capability to meet peak, one of our member countries at one time had no generation of their own. They had all broken down, but they managed to supply the customer without load shedding, getting power from the neighbors, which is very good. That's the security of supply. In my home country, Malawi now, one of the power stations is down because the dam was washed away. Because of that same adverse weather condition, there was a cyclone. But since they are not yet interconnected, I was there about 4 weeks ago, there is a lot of load shedding. As a power engineer, you'd even want to hide, not to show people that you're a power engineer because of the impact. You hear people complaining, even at grassroots, about the power supply. So if they were interconnected, that would have been covered by the neighbors. There was a time we had drought in the region. Then South Africa, they've got more coal. They were now supplying their northern neighbors from their coal power plant. That was in 2017. Then now also regional integration and cooperation. You see this picture. I liked it because it's a traditional dance from my tribe. We call it Malipenga. It's a smart dance. You have to put on white, especially when you are a young man, you're about to get married. That's a good stage to be spotted. But here now it was showcased to the SADC heads of states. They were discussing various issues, including power supply in the region. And there was a gala dinner. And as we say in Africa, when we eat together, our hearts also join. So regional integration, reduction of conflicts is also achieved when we have regionally connected our power networks. In Europe, some countries in Western Europe were connected to countries in Eastern Europe on the power supply, even before they were admitted to the EU Commission. So it's good to interconnect. Then the alternative revenue streams. You can take advantage of heating power, then you get Forex, even when your domestic customers pay in the local currency. So it's an advantage to interconnect. I've just shown you this map. It's not updated. I know Egypt is part of East African Power Pool. Somalia also have joined, and South Sudan. But I took it from that source. It's showing our regional power pools in Southern Africa, Northern Africa, Western Africa. Now, what are the challenges of interconnecting? I'm using the word challenges. At one point, I used to say problems, but someone corrected me that in Africa, we tend to be gentle. We call them challenges, not problems. One of them is technical complexity. There are system disturbances for your neighbors. There are some inter-area oscillations because our networks were not originally designed for interconnection. So now they are connected with weak interconnectors, and we tend to experience oscillations, leading maybe to cascaded tripping. Integrating, we may have to invest in specialized equipment like SVCs to integrate our power systems. That's a big cost. Inadvertent energy. This is the energy which has not been scheduled. It's been interchanged amongst our members, but it hasn't gone through our market arrangements. It's like taking away energy from your neighbor, kind of stealing. How do we manage that? Especially now that we are load shedding. If we send the power which has not been scheduled to our neighbors, it also attracts the civil society. They will start now striking, saying we are sending power to our neighbors, and yet we are being load shedded. So there are methodologies to limit and control inadvertent energy. It's a challenge. Governance and coordination issues, it's not easy to resolve some problems or to decide, to make decisions. There are also participation costs. Now, we are here as a power pool to mitigate those challenges. Then the next section of my presentation is about electricity or electric energy. My presentation or my talk today is about interconnected electric power systems operations. There is a lot to discuss about power pools, but I'm focusing on the power system operations. And operations, just like in a factory setup, is basically producing and taking the product to the customer or the consumer. So our product is electricity. How unique is this product? When we compare with tomatoes, our product is unique because it's transported at dangerous voltages, voltages that can kill. We have to mitigate that. It's also unique because it has to be produced as it is consumed, or consumed as it is produced. So it's a challenge for us as the operations people for this product, because it's not easy to exactly forecast the behavior of the consumer, and also to determine what your generators will do. They may trip, they may ramp down. There is talk about storage, like battery storage, but at present is in small quantities. Where I'm working, we've got a solar system. We've got 100 kilowatt hour storage battery, but it was weighing 1 ton. So imagine if you've got 100 gigawatt hour battery storage, it will be 100 tons. Where do you install? How do you move that? The other challenge of our product is that the direction or path of the flow is determined by laws of physics. We've got the Kirchhoff's law, Thevenin equivalent of impedance, and the other laws. So it's not easy. The electrons will follow the path of low impedance. So if I want to sell power from Ethiopia to Kenya, how do I direct that power to come from Ethiopia to Kenya and not have that power go to Egypt? It will be determined by the laws of physics. It's a challenge to us. Of course, through HVDC technologies, you can direct it through the settings of your controllers. There is also phase shift transformers. They change the phase angle difference of the voltage at 2 nodes. With that, you can direct the power to flow one way or the other. In the Southern African region, we basically use the automatic generation control. When we set it in tie line bias, we can control the tie lines and the direction. It's a challenge, but we've got solutions for that. Then the unit produced, the kilowatt hour, doesn't have the serial identity. So where I sit here, I've switched on the lights. I can't tell whether it's a kilowatt hour from solar or from nuclear or from thermal power plants in Wange or from hydro in Kariba. So if you're an IPP and you want to wheel it and sell to a third party and to price it a bit lower, it goes there without an identity. How do we mitigate that? Later on, we'll go into the mitigation measures. Actually, that's where we are now. How do we term this uniqueness of our product, electricity, in an interconnected power system? I'll start with that first one of dangerous voltages, which can kill. We mitigate or term that through abiding to our codes. There is the grid code, which is normally the jurisdiction of our energy regulators. At utility level, there are also safety codes. If you're authorized to switch high voltage, you have to be trained on the job, you have to pass the training, and be appointed as a senior authorized person. And you will be limited to the equipment you've been trained. There are also operating guidelines and procedures. We've got protection systems that they also mitigate these effects we may obtain from dangerous voltages. Some equipment has foolproof design in them. You can't just open an isolator before you open a breaker. Then there are clearly visible marks in our substations and signs, and access is restricted. Then producing as the product is consumed, we normally utilize operating reserves so that we are ready in case the customer demands more. We've got online capacity ready to take up that load. We do forecasting. There is the accredited capacity obligation. There's a slide about that one. I'll go into detail. Of course, we've got those pumped or those storage facilities. There is also automatic load shedding. If the supply side is constrained, we can then take off the load automatically so as to safeguard our power system. There are also markets in real time. About the direction of flow, basically, I've already explained how that is mitigated. Not having the serial identity, we've got metering. There are methodologies to mitigate imbalances on tie lines. There are also transmission pricing methodology to make sure that owners of the assets are adequately compensated. And also through the market arrangements, the producers are adequately compensated. Then on a bigger picture, we've got this big interconnected electric power system. How do we mitigate those challenges? I said complexity, etc. We may divide our pool into control areas, or we call them balancing responsibilities. We set transfer limits on interconnectors. There are standards to be followed by all TSOs and control area operators. We've got operating guidelines, compliance and penalties for not complying. Then for system disturbances, they are reported, investigated, mitigated, changes made. We also have to be vigilant in terms of monitoring and control. We may use modern technologies like SCADA systems. We have to do maintenance as required and have plans to restore the system. So in operations management, there are a lot of procedures to mitigate these challenges. For inter-area oscillations, we can tune our power system stabilizers, our automatic voltage regulators. We can have equipment with power oscillation dampers. We can strengthen the interconnectors. We want to build more interconnectors. And we can implement special protection systems to detect these oscillations and separate our interconnected power systems. For inadvertent energy, we've got the operation. We have to abide by operational discipline, especially tie line control. Then have maybe software to do data reconciliation and the settlement, financial settlement. So all these, I'm saying, mitigations, they are also subjects, Engineer Lumumba, of talks for another day. Control area divisions, transfer limits, what criteria we use, what studies we take. In the future, we may talk about this. Maintenance, how we do maintenance, how we coordinate, how we tune, how we impose penalties. In SAPP, we've come up with short but very clear guidelines for mitigating all these challenges. That's why up to now we stand as a power pool, and we can't tell when we had any total blackout. We've had some national blackouts, but not a blackout of the entire pool. But in preparation, we've got a restoration plan for the whole region. Okay, so this is like the last quarter of my presentation. Having talked about these mitigation measures for the big interconnected power system, and also for mitigating the unique product, I just selected 3 to slightly go into detail. The rest are for another day. So I selected accredited capacity obligation, 1. The other one, I selected reserves. Everyone talks about operating reserves. So I'll go slightly deeper on the reserves. That's the second one. The other one is system disturbances. A lot more detail about these 3, then I will conclude. Accredited capacity obligation, maybe some of us are hearing that for the first time. It's an obligation. All operating members have to abide by that obligation. I'll first talk about the capacity reserve. This is not the same as the operating reserve. This is the reserve for generation. So as a country, you forecast that in 3 years' time, our demand will be growing at 3% per year. Then how do we meet the demand in 3 years' time, 5 years' time? Our energy regulators are supposed to monitor this so that we are not taken by surprise that our load has surpassed our production. So our guideline in SAPP is that if you're having hydro, at any given point in time, you should have a reserve of 7.6. If you've got 100 megawatts generation capacity or demand, you should have 107.6 megawatts of generation capacity. If you've got a combination of hydro and thermal, you calculate a weighted average. These days, wind and solar are coming in. We do not have a figure of the generation reserve for this renewable energy. Denmark, they are proud to say at one time they supplied all their demand by renewable energy. It's because they've got a strong interconnectivity with their neighbors. If we don't have strong interconnectivity, there is a cloud cover, we may sink, have a total shutdown. Even if you've got a reserve of 50%, it takes how quick the conventional generators are to cover for that decrease in your solar production, and how strong you are interconnected, how your customers will assist in taking off their load, how quick they will do that. So we have not set any figures for generation reserve. Studies have to be done, power system simulations, and each network is unique. They will decide their own reserve. We do get questions where people say, hey, in SAPP, what's the percentage of reserve when I'm using wind or solar? There is no straight answer. You have to study your network, how strongly is interconnected, then how quick are your automatic systems. Then come up with your own strict guidelines to apply to. Some generators have been constrained. Instead of generating 100 megawatts, maybe due to boiler constraints, maybe they only generate 80. In that case, we don't have to declare a bigger figure. We should be working, when calculating these reserves, on the limit where our generation can go to. Now, how do we meet our system peak demand? Priority is to our own supply, even when it's slightly expensive, because we've got our own people, our own citizens working in our power stations. So even though the technology is a bit expensive from the market, we still deploy it because we have to bring economic activity to our citizens. Then bilateral contracts with our neighbors, competitive market, up to the point where we now meet our peak demand. Now, this animal called the SCO, Accredited Capacity Obligation. It's also to do with how you meet your peak, but not the instantaneous peak. It's how you meet your peak for the month. We have now just started in November. Someone said it's a month to remember, November. What will be our peak demand? Will it be 1,000 megawatts? How will we meet that 1,000 megawatts? Our own generation, participation imports, bilateral imports. We've got some capacity we can interrupt. Then we'll go into competitive market. That's how we'll meet. If this is less than what's on the right-hand side, we've got a shortfall. In SAPP, when you've got a shortfall, you are penalized because you are leaning on your neighbors. So on the right-hand side, the supply is taken by your system peak, by your exports, but you also have to keep reserve. So we monitor the peak you meet in that month. Then we also compare the supply side. If there was a shortfall, we've got offline systems in Excel, then we calculate the financial penalty. It's just that in an integrated power system, it's like you are holding each other's hands. So if you don't abide by this accredited capacity obligation, you can collapse the whole network. Okay, so the second one, second from last, is the balancing of production and consumption. This is the one which is talking about the reserves. Of course, you have to balance the supply and demand. And our indicator is the power frequency. At nominal is 50 hertz. Imports and local generation on the left. On the right, we've got the exports, losses, and load. When they balance, your frequency is around 50 hertz. If they don't balance, your frequency will be lower. The green lines you see here, this is the normal band. Our frequency is expected to be within this band. If there is a sudden change, loss of our biggest contingency, which is a generator of capacity 930 megawatts, nuclear power plant in South Africa. Studies have shown that we can only dip up to this point, 49.5. Or if we've lost an equivalent load, the frequency can shoot up to 50.5. Multiple contingency, loss of the HVDC input from Mozambique to South Africa, about 1,800 megawatts, we can drop up to this level. That's how our system has been tuned. So if we lose like only 300 megawatts, the power frequency goes below this point. It's something we investigate because we don't expect that one. We come up with a report and mitigation measures. So we've defined our reserves. We've got instantaneous reserves, regulating reserves, quick reserves, and slow reserves. These terms are from the US. In Europe, they use the primary reserve, secondary reserve, and tertiary reserve. Same purpose, though. So the instantaneous is the one which is localized at our generation plants. So our requirement is that every generator with a capacity of 5 MVA should have an operational governor. That's the one which provides instantaneous reserve. A sudden change, the governor will operate, bring in more mechanical power to balance now that shortfall. It's localized. I always get questions saying, who controls frequency in your interconnected power system? And the answer people give is that it's ESCOM, because they've got the biggest generators. But for me, for us as the coordinator, we say everyone participates. Under instantaneous, under regulating, under slow reserve, everyone participates in controlling frequency. Of course, ESCOM having the bigger generator, bigger reserves, the impact is bigger. The regulating reserve, that's the one which is for minute by minute changes. Someone switches on their water heater, their maize meal, then we use the regulating reserve. And the regulating and the instantaneous have to be online. The quick reserve can be synchronized within 10 minutes, is part of operating reserve. Then the slow reserve, now those are the units which take maybe 30 minutes, an hour to come, 6 hours, slow reserves. So the instantaneous reserve, they control this dip. Instead of collapsing, they will contain it to a certain level and go to a certain steady state. Then the regulating reserve will now peak from the here to the normal band, which is within 50.15 and 49.85. And this regulating reserve uses AGC. It's normally centralized from your national control center. You send the commands to your power plants to regulate, to pick up, to cover for the slow but regular short changes, like these ones. So you'll be having short changes. These are now contained by the regulating reserves. This is an example of a typical daily load pattern, our peak being around 18 hours, then there's another morning one around 7 hours. Then I said there is a dead band. Our frequency, all our power system controllers have been set to control frequency within 49.85 up to 50.15. But we target 50 hertz, the nominal. So you see here, this is a typical plot on a particular date. The frequency went outside the dead band, then our controllers now kicked in to bring it back to normal. And we want the frequency to be within the dead band for over 99% of the time. We don't have to be at the lower point in case we are caught by a disturbance. We have to be within and the set target being 50 hertz. That's the scheduled frequency. We do monitor how the power frequency is controlled by our control area operators. It may be like this sharp. If we control it exactly at 50, it will be a straight line here, this pointing. It's not easy. It's like you want to drive from work home only at 50 kilometers per hour. In all those curves, all those traffic lights, it's not easy. The same with our power frequency. You can't control it exactly at 50. You then strain your controllers at the power stations, those governors, the mechanical systems, the wear and tear will be increased. Hence, we brought this dead band. At the same time, we don't want to have this flat curve with standard deviation of 2. It means you are always outside the dead band. So in SAPP, we've got a standard. We call it CPS1 and CPS2. It's embedded in the SCADA systems. The algorithms were already done, and they report on how good we control the frequency within the dead band. And if the 3 control area operators in SAPP, if they don't comply, if they fail, there are penalties imposed, warnings, and it also goes to financial penalties. Gladys, maybe just to check, Gladys, how am I doing in terms of time?
You have 10 minutes.
Thank you. I thought so. I'll speed up. So talking about the reserves, how are they deployed? In time, the instantaneous one is in milliseconds. an event happens quickly, we want to respond and correct the discrepancy. Then milliseconds or so, close to a minute, the regressing reserves come in. At that time, the instantaneous reserves are released to now get them set for the next disturbance. Then those quick reserves which are offline, they can be now synchronized. So all these up to quick reserves are operating reserves. Then going forward, after 10 minutes or so, we now dispatch the code reserves through market arrangements, or we then run those the generators which were offline. Then there is a formula we used to calculate the operating reserves. There the formula is based on the total demand, the capacity of your largest unit, and so forth. The advantage of the interconnected power system is that, for example, we target 150% of the largest unit. In our case, it's a unit of 930 megawatts. If it trips, the power system will not shake because we always keep reserves, and we target 150%. So in South Africa, they would have been keeping 1,395% if they were not interconnected. But since they're interconnected, we share, and they have been allocated only about 1,000 megawatts. Now that's based on the formula we apply. So you keep less reserves when you are interconnected. There are some who don't have capacity to keep reserves. They can get that from their neighbors. They can negotiate. So we'll now respect those bilateral arrangements. Then what's now coming up, even in our region, now that we are bringing in solar power plant, is this which was researched and found in California from the California Independent System Operator. Kind of a potberry. It's called the dark curve. This is around the 6 hours, and this is around the maybe 17 hours. So the power from our conventional generation is reduced when the sun is shining, because we are deploying now solar. But when the sun is about to set, you now need to deploy more from conventional generators. And it also coincides with the evening peak. So during this time, you have to synchronize as much power as you can to quickly meet your demand. We've had disturbances in SAPP because we didn't deploy our generation as quickly as we could have done during early morning peak or evening peak. We've not reached this big potberry, but we need to prepare. It will be coming now that we are installing more of the solar PV power plants. The last part is about system disturbances. About interconnected power system operations, we can't just go without talking about system disturbances. They may come from your neighbor. Your network may collapse because of your neighbor. In Europe, they've got a regional regulator. It's better. In our upcoming power pools, we've got gentleman agreements. We've got guidelines. We've had some power systems which collapsed. A fault emanating from the neighboring system. Big transformers being damaged because of faults emanating from their from neighbors. We need a regional regulator so that we compensate for those losses. We've got a dispute resolution procedure, but we do agree at pool level. We haven't gone to the point of inviting arbitrators. So a system disturbance is defined as an abnormal condition, which can lead to equipment damage, supply interruption, interrupting also energy interchange. But since the interconnected power system is big, the focus is only those that interrupt power amongst the member utilities. So when we report, we don't just report power loss to maybe some small towns, but if they're affecting the member utilities. The other criteria is when the power frequency goes outside this band, because our power system has been tuned to be within this even during multiple contingencies, 50 plus minus 0.5 hertz. One of the National Control Center managers were saying our generators will keep on tripping. I thought it was unfair to say that, but that's exactly what happens. Every now and again, we've got generators tripping, but we contain them because of those reserves I presented. Okay, so scrolling now, these are the main causes of disturbances. The recent one are also to do with load shedding. While we load shed to balance demand and supply, it often also introduces disturbances. In South Africa, they've got a procedure for load shedding. If they say we are in a level 4, they take out like 4,000 megawatts. That has to be coordinated. If it's taken at the same time, it leads to low frequency situations. High frequency situations. If it's brought back in service, same time, it leads to low frequency situations, at times leading to tripping of some of the generators and the power swings. Then the wind power plants, they are good. Their marginal cost is low. We had a big system disturbance because the IPPs didn't want to reduce. They kept on pumping power. It was around midnight, and then our interconnectors were overloaded, a big disturbance. So the last two are the new emerging disturbances, which we are investigating and coming up with the mitigation measures. Because going forward, this load shedding and the surplus power from wind power plants will give us problems, but we are now researching and coming up with mitigation measures. Other causes are common, like vegetation, human error. Where is the birds and animals? We've had monkeys going into high voltage substations, throwing wires on bus bars, belts on insulators. When it comes to politicians, if there is a power shutdown because of monkeys, it's electrocuted. We keep that monkey because the politicians, they don't believe us. So even if there are lizards in the closed 11 kV panels, when they're electrocuted, causing a blackout, operations people keep it to exhibit. Otherwise, we'll be in problems with politicians. So for every disturbance, we report as soon as it happens to neighboring control centers, then to the coordination center within 48 hours. Then we study it. If it's a very big, we come up with teams to investigate and come up with a big report. Then each disturbance should have a preventive action, a mitigation measure, which has to be implemented, and we track progress for that. Equipment maintenance is very, very important. I attended a certain meeting in Europe. They were saying in one African country, in the local language, they don't have a word for maintenance. And that country is Malawi. I think they did know that I'm from Malawi and I was attending that workshop. They say in our local language, we don't have a word for maintenance. So for maintenance on power systems, we establish schedules, we coordinate. We don't want to take out equipment at the same time. We publish so that we also liaise with the market operations. We inform all. If there is an equipment outage, we give notice at least 2 weeks, and we advise on return so that we can resume our trading activities. If it's cancelled within 24 hours, we assume it went on. For forced outages, we don't have to give any notice. We just proceed and isolate and work on those forced outages. Most member utilities, they hide behind forced emergency outages. They will say there is a big, there are hotspots, but we'll take that out on Sunday. But we say, hey, if it's not an emergency, why Sunday? Why can't you give this 2-week notice. I'll end here with this picture. Someone with a product. For us, our product is very unique. We can't cut it like that. Thank you very much. I end here. Thank you for your attention.
Thank you so much, Engineer Zimba. I was almost clapping actually, forgetting that this might not be the right forum. But yes, thank you for the presentation. That was quite a significant amount of knowledge shared. And yeah, for the members present, we had indicated earlier that you can share your questions via the chat, and I think we have one. I'll begin first with a comment. And Elio Rico says, I follow a Twitter bot that updates the electricity mix in Britain. Would be good to see how it is able to determine which percentage of the national mix they draw from solar, coal, hydro, and the several other sources they have. Are you aware of that, Engineer Zimba? You're speaking on mute.
I missed part of your comments. I heard the mix. I'll be attentive now.
Okay, no worries. So let me read it again. So it says, Elio Rico says, I follow a Twitter bot that updates the electricity mix in Britain.
Okay.
Would be good to see how it is able to determine which percentage of the national mix they draw from solar, coal, hydro, and the several other sources they have. I'm just putting across that. Would you be aware of this arrangement?
No, not that portal, but I know several countries have got a mix. Some will lean more towards the fossil fuel, others towards hydro. But we see going forward, there will be a big contribution from the renewable energy. That's where I said, to what extent can we have renewable energy at the expense of the conventional? We need to maintain the inertia because the renewable energies are intermittent, but it will depend on the uniqueness of each power system. If they are heavily interconnected, they can go all renewable in real time. Something happens, they get from their neighbors. If they are not, then they need to reduce on renewable energy. They also invest more on automatic systems. If there is a cloud cover, it happens within seconds. They should pick up quickly. So I don't follow that portal, but if I think it would be interesting to see how our colleagues in Europe are also managing this. Thank you.
Okay, welcome. Just to put across also, Elio Rico, if you were able to share the link as requested again by James, it would be great. And for the benefit of all members, we are recording this session. We shall have it uploaded in our YouTube channel once we are done with the recording. And yes. So proceeding on, there's another question here from James again. And James is asking, what penalties are meted out on participants who break the terms of power pool agreements?
Yes, at operational levels, we noted that our operating guidelines didn't have the teeth to bite. So in 2010, members were leaning on each other, just drawing power from their neighbors, not controlling the tie lines, not controlling the voltage well, not reporting the disturbances. And since we don't have a regional regulator like they have in Europe, we said, let's give teeth to our operating guidelines. So we put in penalties for lack of discipline. But our penalties are not that punitive. They just like say $1 per your peak demand. So if your peak demand is 200 megawatts, it's like $200. But we just wanted to highlight, because we know at utility level, payments are authorized by senior people like top management. So top management will be aware that they are paying that small amount. The highest will be $2,000. Some members have already started paying. We implemented in 2016, and the monies, they come to the coordination center. Those who are in the wrong, they also benefit because the monies come to the, some were saying they should not benefit. It was not easy to implement that. So the funds we get contributes to the operation budget of the coordination center. But if all is well, we need to utilize our legislation, not our operating guidelines. Hence, we need a regional grid code. If you have damaged your neighboring member's transformer, the grid code should have the teeth, should have mitigation for that. I hope it has addressed that question. Thank you.
Yeah, I think that's addressed, but I was just wondering to myself whether how the biting is done, because you realize again that sometimes some members can just decide and proceed with the way they've been working, and cascading the problem again 3 years, 2 years, or even a decade between that. So a follow-up question on that is how are we doing this? How are we meeting this condition on the member states? What is the procedure? Do we have a position where we say, okay, you have done a bad job for the past 1 year, we are cutting you off? Where's the teeth? Where's the teeth actually?
We noted that since the amounts are low, some members can ignore everything and just budget that for this year, this is what we are budgeting for the financial penalty, maybe $1,000. The following year, $1,000. But we use like name and shame. So as we report to the management committee, to the executive committees, we do highlight that this utility has not complied in this category. So we use that name and shame. And then we encourage them to be coming up with mitigation measures. Others have applied for exemption. Then we do sit and see whether it's worth it to give them exemption or not. The last one we had, we turned it down because we thought it would give a wrong precedence. So we also give congratulatory letters. So every year, those who do very well, they will receive a congratulatory letter. So it's not only on the negative side. But it has assisted because the executives, top executives, they don't want to be said to be not complying. So they do press at operational level to their utility to comply as we wait for the grid code, regional grid code. Thank you.
Okay. Thank you again. I think that is quite addressed well. So on to the next question that is from Oliver Mandala. He's asking, how is SAPP and IEEE Africa handling the problems that come from transmission constraints?
Okay, thank you. My presentation was not on the planning and the power system development, but it's from that function where we handle the constraints. We need to build more interconnectors. In SAPP, we received a grant from the World Bank and we set up a project advisory unit. They are now assisting to move the projects up to the bankable level, and then you now take it up to development of the project. So those will relieve the transmission constraints. Then some of us are in real-time operations. We can't wait for new interconnectors. We have to make do with what we have. So we identify which corridors are constrained. We do power system studies, advanced power system studies, many using PSSE or Dixon Power Factor. We used to do that at the coordination center, but some were disputing. So we invite owners of the networks to a workshop, maybe a week or two, because they know their networks better. We do the power system simulations, and the output of that are what we call transfer limits. So we set transfer limits in both directions, and we take these to our market operations. When they're concluding their trades, they will not overload the interconnectors because they are limited by the limits we set. And these limits are not to do with the thermal capacity of the conductors. Often you may have a line like with a capacity of 750 or 1400 MVA, 330 kV line. You find that our limit may be as low as only 200 megawatts, because we consider stability, transit stability, and the impact on voltage. We want that when we are transferring that amount, in case the parallel route trips, we will not collapse totally. So we've got a procedure for determining transfer limits. And then there are counter flows, trades going southwards and also trades going northwards. We are happy when we have those, because eventually it's like having a zero. If you got 100 this direction, 100 that direction, we've got a net zero. Then we can put on top of that one another 50. So with the knowledge of our network, we make do with the resource we have, so as to promote the interchange of energy amongst our members. We want to optimize our networks to their benefits. The more we trade is to the benefit of the investors and to the common man in the village, those who have who are our customers, the consumers. Thank you.
Thank you again. That was, I think that is quite addressed. Next question comes from Momo, and Momo is asking, do coordinators of the pool always survey the network infrastructure of a country before allowing them in? For example, ensuring they are less likely to cause disturbances due to equipment breakdown. Is there due diligence from the part of the persons who are to do the interconnection so that they ensure the infrastructure from the incoming team is sound?
Yes, that's done. Presently, priority is to interconnect those countries that are isolated, like Angola, Tanzania, and Malawi. So we've done several studies, and we've decided how we need to connect them. We know it will be smooth connection because we've done studies, and from those studies, we've come up with the designs. So that's the first level, connecting the national power utilities. We know how to connect them smoothly based on technical studies. Then for IPPs, we do that due diligence. They apply that they want to be members, they want to interconnect. Before they apply to be members, they will have already interconnected, most of them. They deal with the TSO where they are based. Here in Zimbabwe, they will be dealing with the ZETDC or ZESA. And then they come up with an interconnection agreement. If you are to interconnect, you should have an isolation point like a breaker. You should be monitored, maybe sending signals through SCADA to the regional or national control center. Then you have to be doing your forecast. Then you should have people authorized to do switchings at high voltage level. So all those, they go into the interconnection agreement. And then you have also to participate in voltage control. We noted that most of these IPPs, they focus on the megawatt, the real power, because that's the one which is charged, not on the megavars. So when they connect, they may introduce low voltages there. So through system studies, they are forced to compensate for the low voltages or high voltages. And those, they go into that interconnection agreement. It's more like a technical document. Towards the end, of course, there will be now commercial stipulations, like how they will be trading. So at low level, that's done with the utility they are connecting to. So having connected, if they want to be a SAPP member, they then apply. We then go set up a team to do due diligence, and then they make recommendations to the management committee, whether they will take down or not. If you go to our website, there is a procedure, there is a document if you want to be a member. It came from the ministers of energy, that is SAPP opening up to independent players. So we came up with a procedure. It's posted on our website, and we've received a lot of applications. Some are just walk-ins. Most of them, they just waste our time. They really don't know what they want. They'll say the power lines are already close to us. but they are pointing at a 400 volts line, and yet they say want to bring in a 100 megawatt plant. And the others, they want our no objection so that they access funding from the banks. They say, as SAPP, can you commit that you take our power? So our management looks at all those applications, the due diligence is done. So for us in the power system operations, we're interested in how smooth the networks will be when they interconnect, especially the voltage, the reactive power support. We don't want the generators just to be focusing on the megawatt. When they focus on the megawatt, there is big efficiency for their power plants. That's what they want, but they should also assist the interconnected power system. Thank you.
Yeah, that was quite detailed. Thank you. I guess Gladys, you answered. Then the other question, I think, from Roda Baheireo, sorry if I mispronounced that. Not clear actually the question. Then she actually says, thank you so much, Engineer Sydney. Can power pools be further interconnected? I don't get the question.
But I get it.
Okay.
There is a program to interconnect Southern African power pool to East Africa power pool through the Zambia-Tanzania interconnector. Construction has already started on the Tanzania side. It's about to start on the Zambian side. And it will be an AC interconnection. I will still maintain my opinion that I wish that interconnection was HVDC, because I do experience power oscillations within the Southern African network on its own. What if we connect Eastern Africa power pool through one 400 kV line? We'll be having those power oscillations. There will be more work. We will need more power engineers. It would have been better if we had used an HVDC back-to-back. But HVDC is very expensive. Maybe we couldn't have waited for years. It's better to have this lower cost solution. Fine. So the power pools will be interconnected. Eastern Africa already goes all the way up to Egypt. Egypt crosses the Mediterranean, I think, is the Red Sea, connecting into Europe. I think Morocco also does that, northern side. And then the African Union Commission, based in Addis Ababa, they launched the single electricity market for Africa, a program to achieve that. So they are working towards that, and we are involved as SAPP. We've been participating in workshops. We have been trained to prepare for that single electricity market, such that if you are based in Ethiopia, you can sell power to South Africa. You are based in maybe Botswana, you can utilize power maybe from Egypt. That's the desire. Our colleagues in Europe and America, they have already interconnected their continents. And we also want to go there. And we don't want to go round and round. We want to use a simpler solution to learn from what they've done. So in the future, we'll have one network in the whole continent. And maybe that will develop our continent more economically, especially with this view that we want to exploit the Grand Inga and other big resources, energy resources we have in the continent. Thank you.
Okay. The next point here is a comment from Erico, who is saying he made that comment about the Twitter board because engineer mentioned that we are struggling to know whether you're consuming power from coal, so I mean solar, hydro, or wind. He has also shared a link. I think we shall be posting that again in our description once we're already ready. So there's another question here from Oliver, and Oliver is asking, are there deliberate measures put forward for upcoming interconnector like for TANESCO and Angola so that we don't experience transmission constraints 10 years after commissioning? Are there deliberate measures put forward for upcoming interconnectors? Okay.
Yes, there
can
are.
proceed.
There are, and on paper, we are heavily interconnected. The only missing link is the funding. But on our shelves, we've got a number of reports giving us a picture of the African interconnected power system. There are a lot of interconnectors with a lot of acronyms. We've got Mozisa, we've got Zizabona, we've got ANA, that's Angola, Namibia. We've got the other one from Angola to Namibia to Congo. So on paper, we've got a lot. So the missing link was the funding, and hence we've got the project advisory units that are assisting in packaging the projects. Then there is also talk about having our own funding. The money we make from the trades, we can now use it and have some equity in some transmission projects, more like a private company. Yeah, thank you.
Interesting. Yeah. So another comment again from Helen. Helen says it's been an eye-opening presentation, well presented. Congratulations, Engineer Zimba.
Thank you.
Now, another question again is this is from Suma Lungu. Do interconnection agreements allow for one utility to have more than the tie line SCADA visibility for purposes of short-term operational forecasting? For example, unit availability or internal constraints that might affect trading.
Yes, so at utility level, they do push to have that visibility so that they are observing what's happening at the source supply end, what's happening at the transportation or transmission side, and also at the distribution end. So the more visibility you have on your power network, the easier it is to control it. That's at utility level. And the question is, when you are interconnected, do you still have that visibility of your neighbor's network? Traditionally, the neighbors do not want other people to see their bedrooms. So as SAPP, we are trying to open up that please give as much information to your neighbor as possible. If you are an IPP, you want to interconnect, that's a good opportunity to say, if you want to interconnect, first, establish a link with our control center so that we observe what you are doing that side, so that we can also assist you in case you've got problems. Then, like I reported, we had an event where the wind power plants in South Africa, they were generating over 2,000 megawatts. And it was a big access on our interconnectors tripped. So visibility is important. There is a lot of talk about confidentiality, but if we are to develop further, we need to relax some of these rules about confidentiality. There are times when we go to workshops, some of our members, they don't want to give us documents. They say they are confidential. We actually have to use the good skills on Google. We find that the same document they were hiding from us, if you are good at Google, you still find it. At times you find that it's on their websites already. And yet in the meetings, they don't want to give us those. So visibility is important for operations, and it has to be encouraged, both at utility level and then at IPP level, and also coordinating with the neighbors. Thank you.
A very informative session, actually. This is a comment from Anthony. Thank you again, Engineer Zimba, Lumumba, and the team. Well, yes, that was quite, that's the end of the comment section and the questions we had on chat. But I also have, I think, two. I know we are 3 minutes into the hour mark. And just for you, Engineer, I want to know, do we have a way of tracking such good points as regional integration in terms of the benefits that it brings? Other than just saying we have connected Power Pool 1, 2, and 3, is there a way of measuring the impact of doing that as far as regional integration is concerned?
There is, but in my view, it has to be done by the economic blocks. We've got SADC, we've got the East African Community. We are into the power systems, but the advantages may reflect in other sectors like trade and industry. You find that we've increased production in one side because of the ability of power supply. So the tracking, in my view, has to be done by the economic blocks for the benefits. Us at power pool level, we have to track now the stability. Having connected, have we made the reliability lower, or we've made our system less secure? How do we mitigate that? Like I said initially, that our networks were not designed for interconnection. They were designed for local loads. If we are now to interconnect, we need to update maybe our control systems at the power stations, like the power system stabilizers. We may have now to bring in specialized equipment like SVCs at interconnection points. So for us, the tracking will be more on the whether we have increased the ability and the security of our power supply. That has to be tracked, and we may be assisted by energy regulators. I know they focus more on power quality like harmonics, interruptions, but they may also have to increase their monitoring to monitor these benefits. Yeah, that's my comment on that. Thank you.
Well, great an answer that is. And at this point, I would pass it over to our team lead. Thank you again, Engineer, for the opportunity to be with us. And Bonalumba, you can take over from there.
Thank you so much, Engineer Zimba. Thank you, Newton, as well, for steering the ship. Just a quick one. This is an addendum, even as we are just on the top of the hour. I've posted a link in the chat to a conference that is upcoming next week. This conference is targeting students and young professionals in all, STEM sectors. I'm going to just share my screen quickly. I want to ensure that all of you have a view of this, because it's going to be useful to anyone who's at least in this meeting today or is interested in matters STEM and engineering going forward. So let me share this. Yeah, so we are having the Kenya Students and Young Professionals Congress. It's happening in Nairobi, Kenya on the 10th and 11th of November 2022, that is next week. And it's a full 2 days of learning, growth, research, industry engagement, and interrogations and integrations with different professionals in different industries. So if you haven't known about this, or if you haven't registered to participate, please do. This is going to be one of those landmark activities and congresses that are going to be annually running, sponsored by IEEE and integrating other partners as well. This time round, we didn't manage to get SAPP on board, but now that we have Engineer Zimba, and he has been part of us now, I think next year we'll definitely have SAPP and other power pools well represented. But yeah, check that out. It's in the chat. I've shared the link. And without further ado, knowing that we are short on time, I want to thank you all so much once again. Thank you, Engineer Zimba, for the wealth of knowledge. We look forward to engaging you again, and the larger, power pools team that you work with. You're doing a lot of work for this continent. I'm looking forward to when AFCFTA works with you guys to build that single electricity market and the transformation that brings going forward. And I know you have a flight to catch after this, so thank you so much. Thank you, everyone. Have a good day. Stay winning and stay African.